Okay, great. Why don't we go ahead and get started? So welcome back everybody to EE240. Just a couple of sort of administrative slash informational things. So I did post the homework over the weekend. By the way, how many people actually already took a look at that? Anybody? Oh, good. Started? Okay, good. So definitely by the end of the day, you'll be able to do, sort of the first two problems. The last one you can actually sort of do even now. But there's some terms and things that we're going to kind of go over in lecture probably on Thursday or so. So it'll sort of make more sense as to why I'm asking for those particular plots. But basically, that should be you should be able to start. Is there a question? Or?
Where's the course website again? I can only
Oh, so just instead of it, Spring '09, the thing at the end is S09. Just change it to SP10.
SP10.
Yeah, that's right. Yeah. Okay, so, as I said, definitely go ahead, take a look at the homework. You should be sort of capable of doing almost everything fairly quickly. Another question in the back there? Or?
I just want to talk about it now. I was going to ask about the discussion session.
Yeah, no, so I'm going to talk about that right now. So the other thing is, as I mentioned, I twisted a grad student's arm to kind of help out with the class. Again, he's totally volunteer, so be nice to him. That's Pierluigi Nuzzo. He took the class last year, did very well, so I'm sure he'll be able to help you guys out quite a bit. And the reason I do that, by the way, is just because I do think it's a good idea for you guys to have somebody else to just kind of come and bug and bounce ideas off of and things like that. I'm, of course, always available, but, having sort of two avenues is a nice thing to have. So from that standpoint, Pierluigi is going to sort of alternate between, in some sense, discussion sessions and office hours. So one week, usually when the week the homework goes out, he'll sort of do a pseudo-discussion session, meaning he'll kind of cover things related to the homework or maybe just review some of the material that I thought maybe wasn't entirely clear. And then in the other week, he'll sort of hold in office hours during that time, just in case there's any kind of questions and things like that. So for this week, we're going to do it tomorrow, Wednesday, from 3:30 to 4:30 p.m. It's just going to be over in 550 Corey, kind of in the lounge area, in the corner over there. If you've ever been there, I'm sure you know what I'm talking about. If not, you'll figure that out pretty quickly. So we're going to do that then for this week. And so the only sort of residual question is Wednesday 3:30 to 4:30 a good time in general, or the only other option we have right now is probably Tuesday 2 to 3 p.m. So maybe we'll just take sort of a quick vote. So who thinks Wednesday 3:30 to 4:30 is better for them? Okay, now I guess I'm going to, looks like mostly. Anybody really strongly prefer Tuesday 2 to 3? Okay, class or something like that? Just prefer. Okay, so in that case, I think we'll stick with Wednesday 3:30 to 4. That is obviously, I guess, closer to when the homework is due, but given that that's the case, I suppose that also means that there'll be more of you that actually have questions, so perhaps that's the right trade-off to make. So again, we're going to stick with Wednesday 3:30 to 4:30 p.m. That'll be basically every week. And Pierluigi will be there. For this week, he'll kind of just cover a few things related to homework number 1, and then next week he'll sort of hold his office hours. So any other kind of questions on logistics sort of things or material or anything like that so far? Okay, good. So with that, let's dive back into where we were. So I believe where we basically ended up last time was sort of kind of wrapping up on resistors. And so maybe just to briefly remind everybody, we'd gone through sort of all the different layout mistakes and all the sort of issues with actually building the resistors. We kind of just talked really briefly about how you can use Mosfets as resistors. And even though you can, they obviously kind of suck from the standpoint of having any control over what their actual value is. But we talked a little bit about how in certain applications that may not really matter all that much. So as an example, if you just want to use it for something like setting a bias current somewhere, or maybe setting like a time constant that you don't really care if it varies by a couple orders of magnitude. Those are all sort of reasonable things to do with a MOSFET. And again, the sort of real advantage there was if you wanted to get really, really big resistors, you could do that with a MOSFET basically by using a very small VGS. In fact, in some applications, things like, let's say, high-pass filters, so let's say something like that, where let's say you just want to AC couple the input of your amplifier or something like that. So you want to be able to set this DC voltage independent of where the input is sitting, but you still want to get a pretty low frequency signal in. Well, there's a couple things you sort of have to have, right? Well, maybe I'll even ask you guys. So if this is something that I was doing, what would set sort of the lower cutoff frequency? I'll just give you maybe the components here. So what would that be set by? It's early in the morning, huh?
Over RC?
Yeah, it's just set by 1 over RC, right? So by the way, remember, anytime you see an RC like that, basically anything you're interested in is set by RC. So in this particular case, if I'm going this way, and let's just call that a V bias, right, then it's basically a high-pass filter. And exactly as you said, it's just the lower cutoff frequency is going to be set by 1 over RC. So now let's say I want a really, really low frequency. That means I need a big RC, right? Well, so there's kind of one of two ways I can do that. I can either make a really big C or a really big R. And as we'll see in a second, if I'm going to do that with kind of the quote-unquote standard things, both of those are rather painful. Okay, they just take a lot of space. So again, in something like this, you might take that R. You might actually build it out of, and this is going to sound funny, but you might even build it out of a so-called off transistor. You might just basically tie the transistor up so that its VGS is essentially 0. Because again, you just want a really big resistance. And as long as you don't care what the value of that resistance is, that's a way of getting a really big resistance. Because now you just have leakage current, right? So again, these MOSFETs, occasionally you'll see them, or occasionally you might even use them for resistors. Don't use it for anything where you really care about the value. Okay? Because, from that standpoint, they really suck. But if you want something big, not a bad option to use. So just to again really sort of briefly summarize on resistors before we move on to talk about capacitors, kind of the key point was that, if you're a digital guy, resistance in general is a bad thing. So in most of the processes you're going to use, pretty much there isn't any sort of great way of doing it because they've intentionally tried to minimize all that resistance. So that means that it's going to take you sort of a reasonably large amount of area to get a reasonably large resistance. And of course, not only that, they're going to have all kinds of non-idealities associated with them. So there's going to be big variations in absolute values. They all are going to depend on temperature. They're going to be nonlinear, meaning they have voltage coefficients for a bunch of the reasons that we described last time. So long story short, when you can, you really want to avoid resistors. So especially in things where, it's a really sort of critical part of your design. So as an example, let's say amplifier feedback networks or filters where you need really, really precise time constants. In fact, even in A to D converters, we're going to see that there's this whole sort of style of designs that basically it's doing everything it can just to avoid the use of resistors. So we'll come back to that a little bit more later on, but for those of you guys who have heard of it, you've probably heard of like switched capacitor circuits. Again, a lot of that was done just to sort of avoid some of these issues. Okay? So as I said, we'll sort of get back to that point. But to understand sort of why something else might be a little bit better, obviously next we have to sort of talk a little bit about just capacitors and how we're going to build those. Because again, in sort of that, in all the toy examples that we had drawn last lecture of just different analog circuits, there was a lot of resistors. There was also a lot of capacitors in there, and so we got to figure out how we're going to build those. So let's just sort of take the simplest, stupidest thing we could do and build a capacitor that way. Well, capacitor is just two parallel plates, right? Two parallel conducting plates. So in CMOS, kind of the simplest thing I could think of to do is, why don't I just take a piece of metal, draw that piece of metal or even slab of metal on top of the substrate, and now I've sort of got a capacitance, right? Because there's some spacing between those two things. The substrate is relatively conductive, and so I've got a capacitance, right? So this sort of works, but what's the kind of obvious problem here? Why might you not exactly want to do this?
Depletion layer?
Say that again?
Depletion?
Yeah, well, not exactly. So I didn't really draw where the contact is, right? But this could be P+, and the substrate could be, P, and so there isn't necessarily a depletion layer per se, although you're right, there may be some depletion underneath here, but that's not exactly the issue per se. What else is the issue?
You have coupling through the substrate.
Say that again?
You have coupling through the substrate.
You do indeed have coupling through the substrate. I'm actually getting at something, let's say, much more simple than that.
One side is grounded.
Yeah, there we go. It's the substrate, right? So one side had better be tied to ground.
Oh.
Yeah. So substrate is grounded, right? So if I wanted to do a capacitor not from some point to ground, then this is kind of not that great of an option, right? So sure, sometimes, indeed, I want a capacitor that's just tied to ground. We'll maybe talk a little bit more about that later. But if I actually want a capacitor, let's say, in between two terminals, like in that example that we had drawn before with the MOSFET amplifier that was AC coupled, right, this is no good. Because one side's definitely, actually both sides are not ground, okay? So, okay, well, that's not too difficult to fix. I can always just go and say, okay, well, fine, I've got, multiple metal layers in my process. Why don't I just take basically two of those metal layers and do just two big slabs of those things sitting kind of on top of each other, right? Okay, so now indeed I've got a parallel plate capacitor, and I can independently sort of touch each one of those two terminals. But now, of course, the next question is this really just that sort of capacitor that I had drawn there, or do we have some other stuff happening here?
Bungee fields.
Oh, okay, wow. So you like jumped 2 steps ahead. That's certainly true. So we'll come back to that in 1 second. There was another thing in the back.
Don't you still have a capacitance to ground?
Yeah, you've still definitely got just the straight parallel plate capacitance to ground, right? And as Will just said, not only that, you've actually got, from all of the fringing fields, you're also going to pick up extra capacitance down to the substrate, right? So I don't actually have just sort of one capacitor, but I've actually got, let's say, several. So just to be clear, if I was going to, let's say that this was my model I was going to use in SPICE. So if I wanted to plug this actual capacitor into SPICE, so let's just call this, let's say, top and bottom. Okay, so this is, let's say, top, and let's call that bottom. So what else would you want to add into this model to kind of make it be more reasonable? What's kind of missing in terms of this model here?
Cap to ground on both plates.
Okay, yeah. Basically, I need some capacitance to ground on both of those plates. Now, somebody other than Will, let's call this CT and CB. What's going to be the relationship between CT and CB? In other words, which one do you think is going to be bigger?
CB.
Yeah, CB, right? Because it's got the entire parallel plate thing all going down to the substrate. So, by the way, usually people refer to these things as bottom plate capacitors, even though obviously there's actually quote-unquote bottom plate capacitance on the top plate as well, right? So, if somebody says that, just keep in mind there really is some capacitance from both sides of them to ground. It's just that oftentimes, indeed, the capacitance on the really bottom plate does tend to be larger. Okay? Wow, so that's really good. We actually sort of flew through that. So now, maybe I'll give you the more challenging question. So let's say I really don't want those parasitic capacitors. So I really, really want to just make those as small as I can. Any tricks anybody can think of to play?
Turn it on its side.
Turn it on. Oh, okay. You're getting really sophisticated. So you could indeed do something like that. But by the way, even if I turn it on its side, well, we'll come back to this shortly. So that's kind of, you can build sort of a vertical thing. Unfortunately, in a CMOS process, I don't really get to control that, right? So we'll talk about this a little bit later. But so I could like stack metal layers, but I don't have like an infinite number of layers to play with, right? So if I really want to get a big cap, I'm going to have to start putting these things next to each other. And then I'm actually going to get extra bottom plate, or I'm still going to have some bottom plate to the bottom. Now, you're right, that's actually a really good idea, but I actually had, even with this structure, I claim there's something else I can do.
Load it in its own well.
Ah, okay, so you're definitely way ahead of everybody. So we've got a substrate here, right? So the problem was that all the capacitance is going to that substrate. Well, if I really want to make that small, what I can always do is put an N-well here, right? And then if I put that N-well there, if I'm really clever, the next thing I can do is I'll make a contact onto that N-well, and you'll see why I'm going to draw this big resistor here in 1 second. I'll just give myself some more space. And actually, I can bias that N-well up, right? now somebody other than who has already done this, why would I put this sort of bias thing on there? What's that going to do for me?
You try putting it the same voltage as maybe the bottom plate, so there's effectively no capacitance.
Oh, okay. So you're saying something like I'm gonna, connect bottom over here, right? Or perhaps you're saying maybe even I'll connect it over here. That's actually not a horrible idea, but unfortunately I think that might actually not do exactly what you want it to. So I claim there's a little bit better way. So you were saying something like, well, if the voltage on both sides is the same, then I don't get that capacitance. You're right, that would knock this off. But unfortunately, it would add something else. So what else does it add?
Junction capacitance.
Yeah, it's going to add the junction capacitance, right? Because I've put that N well in there. So now there's just a junction capacitance from that entire N well to the substrate, right? So I'm still going to have that. So now why did I do this bias thing with the big resistor over there? What was the trick I was trying to play? Any thoughts? What happens is I bias the junction relative to the substrate. Let's say I put a positive, like a really big positive voltage on that N well. What's that going to do? So what is like a P substrate and an N well? What circuit element is that? The diode, right? Okay. So I've got my diode. This is, of course, ground. If I start moving this voltage up, what am I doing to the diode?
Breakdown?
Oh, no, I don't want to break it down. That would be bad. But yes, that will eventually happen. So, before that happens, what am I doing to it? Yeah, somebody in the middle, maybe Sharon or Kat, were you guys?
Reverse bias.
Yeah, you're reverse biasing the diode, right? So why would I want to reverse bias that diode? What is that going to do? How's that going to help here?
Lower the capacitance.
Yeah, it's going to lower the capacitance, right? Because as I reverse bias that thing, I'm increasing the depletion region width, which means the capacitance is going to go down, right? That's good news because now, if that cap gets smaller, as long as this resistor was, let's say, big enough, meaning that at some frequency that I'm interested in, it's kind of an open circuit, then now what's the effective capacitance I'm going to get? So let's say that I used to have a CB, and let's say that the total capacitance there is C depletion. What would be like the effective capacitance that I would get?
C depletion.
Almost. I mean, you're sort of right, but just to be more precise.
In series with that.
There we go. It's C depletion in series with the C bottom, right? Which is guaranteed to be smaller than C bottom, right? And in fact, if I'm really aggressive and I put a pretty reasonably nice bias voltage on there, then also I've actually reduced that depletion, and so on the net I can get a pretty darn low bottom plate. Okay? Now there was something that somebody else had mentioned about, sort of substrate coupling. This is sort of also true. I mean, this is what's known as kind of an isolation well. So a lot of times people will do these kind of tricks just to try and isolate you from junk happening on the digital side. There at least isn't any like DC current flowing through here. But by the way, there is still that capacitance there. And so at high frequencies, stuff will still couple in. Okay, so that's why, even from that standpoint, actually doing this biasing trick tends to not be such a bad idea.
Why not put a trench kind of stuff below, oxide?
Oh, you mean actually dig it out?
Yeah.
Yeah, so if I could literally just dig this thing out, then absolutely that would be better, right? Now, unfortunately, I can't always do that, but yes.
Can we go to higher metal layers?
Ah, okay, that's another idea. I could try and go up to a higher metal layer, right? So I could just try and take this structure and move it up to, let's say, metal 6, metal 7. That also actually does work. We'll see in a second that, and actually we can even touch on this now, if I really had multiple layers, how do you think you'd want to build this capacitor? And by the way, this is a part of your homework, so this is useful discussion, I suppose.
Using all the layers?
Yeah, I'd want to use all the layers, right? Because if I had, let's say, 7 layers of metal, then I would want to keep alternating, right? So if that's top and that's bottom, on top of it I'd want to put another bottom, then another top, then another bottom, top, bottom, and so on and so forth, right? Just so that I get each of those caps in between, right? So now actually I didn't put it in the homework, but it's kind of a useful problem for you to go and do, especially if you have to build one of these things. So now you can see there's kind of this trade-off here, right? Because if there's a certain size capacitance I want to get, the more of these layers I use, the smaller physical area that's going to take, right? So that's good. In other words, the density of that capacitor is going to be pretty high. But as you mentioned, maybe it's actually worthwhile to get rid of some of the lower layers just to move yourself away from the substrate. Now, unfortunately, if my size of the capacitance is the same, when I get rid of those lower layers, I actually am going to have to take more space, right? That means that I may not actually necessarily win at the end. Because if I have to take more space, there's now more area for me to pick up bottom plate from, right? So it's actually a very easy or sort of quote-unquote fun calculation to do, to figure out, if I told you what the layers were and what the spacings were and all that, what would be like the best configuration to use if you really wanted to minimize that so-called bottom plate or really parasitic capacitance. Okay? Does that kind of make sense? Or? Okay, good. So now we sort of just have a little bit of an idea. Again, we'll walk through these in more detail. But again, I just want to sort of give you a feeling for what are the capacitor layers typically available to you, and sort of what kind of capacitance density numbers you can expect to get. Okay? Now, as you can probably imagine, the thinner the spacing between the layers, the more capacitance you can get per unit area, right? And so, as perhaps should be obvious, the highest capacitance density you can basically get on any CMOS process is by literally just taking a transistor and tying it up as a capacitor, right? So doing something like basically that. Okay? So just by the way, why is it that I say that that's probably the highest possible density thing you can get? What's so great about that from a density standpoint?
The oxide thickness.
Yeah, the oxide's the thinnest thing you've got, right? By the way, anybody know what kind of oxide thicknesses, roughly speaking, are people talking about today?
12 angstrom.
Less than nanometer.
Yeah, okay, 12 angstroms, right? In other words, 1.2 nanometers, right? Now, physically, it's not actually quite that thin, and by the way, there's all kinds of issues that we'll get into later today when you get to things that thin, but yeah, that's the kind of thin, thicknesses that we're talking about there. So that's why here I've said, this 10,000 attofarads per micron squared, that's about 10 femtofarads per micron squared. Today, actually, you can probably do even better than that. It's probably, well, at least if I could really pack everything just with transistors, it'd probably be more like 20 femtofarads per micron squared. Turns out you can't exactly do that for a whole bunch of reasons, but maybe actually I'll ask you guys, if you wanted to build a really big capacitor, do you think you would take like the entire chip and just spray it with, this super thin 1.2 nanometer thick layer, or no?
No.
Yeah, why not?
Reliability. Pinholes.
Maybe one at a time. Somebody who hasn't spoken yet.
Uniformity issues.
Uniformity. Maybe. Actually, I guess that's right. But I want something much more specific. So I want to be very practical, I guess. What if there is a problem with uniformity? What might that cause?
If there's a defect anywhere, you could have a short.
Yeah. Basically, I've got the thinnest thing I can possibly build, and all it takes is like, I don't know, one dust particle or whatever it is, and the entire thing is shorted out, right? So by the way, if you look at a modern chip, even though there's a lot of area there, the amount of transistor area is actually a relatively small percentage. Because if it was too large, then you'd have really bad yield issues. Basically just, there's a really good chance that something somewhere is going to get messed up. And in fact, if you look at places that have a lot of transistor density, oftentimes they'll have switches they can just sort of turn off, just so that if that part is dead, meaning shorted out, it doesn't kill the entire rest of the chip. So you can still sort of sell the rest of the chip in some way. Okay? So that's sort of the transistor. Sometimes, and I'll talk about this a little bit more later, people have some process option where they give you sort of two poly layers that happen to be close together to each other, so you get sort of pretty reasonable density out of that. But everything else, at least with only a single layer, tends to not be that dense. Okay? So like two metal layers, let's say stacked on top of each other, is maybe about, let's say, 50 attofarads per micron squared, somewhere in that ballpark. Okay? And by the way, this is again one of those things where you as an analog designer really wanted a lot of capacitance, but all the digital guys who paid the $10 billion to get this technology to work don't want any capacitance. Okay, and so for a lot of the stuff, just even if you wanted capacitance, you can't get it. Okay. The other thing is, of course, many of these capacitors, just like with the resistors, are not ideal, meaning there may be some voltage coefficient on there. For Mosfets, we'll talk more about why that happens in a second, but even for the poly-poly, just those depletion regions come into the picture, right? As well as, of course, there could be some temperature coefficient, if nothing else, just because of sort of thermal expansion. Is there a question? Or?
Yeah, so if we're doing a lot of mixed signal stuff on the chip, and you'd think at some point it'd be cost advantageous to do, because it's just back of the line to add mem caps, right? So.
It's a good question. So yes and no. So the question is all about how much volume is there in that quote-unquote special thing that you've done, right? And so oftentimes, in older processes, the trade-off you were describing where, okay, I could either use tons and tons of area in the standard process versus, just build a little mem cap thing, that was often actually a reasonable trade-off. As we'll talk about a little bit more in today's technologies, where I have lots of metal layers, you can actually get pretty darn high densities. And so we'll see how we can actually do that, and that's why it's not as common anymore. But that's a great question. So to do that, actually, let's sort of just take a look at some of our options in slightly more detail. So remember I said, the MOS capacitor was the most dense thing, and so you really wanted to use that, at least from a area standpoint. Well, obviously, because it's a MOS, it's also got all kinds of other issues. And so perhaps the biggest one is it's going to be highly nonlinear. So by the way, how many people have sort of seen the MOS CV curve at least, 5 times or whatever? Okay, good. So that's exactly what's shown here. Just to remind you, when you get close to the threshold voltage, the substrate is depleted, and so you have a relatively small capacitance. And so in particular, if you're trying to use this as a capacitor, and the DC bias across it might indeed be close to 0 volts, you're going to get all kinds of nastiness happening, right? Because you're not really going to get that much capacitance. As the voltage moves around, it's going to be highly nonlinear, so it may not really behave sort of the way you want it to. Now, not only that, of course, but what could happen is that basically the threshold voltage is actually going to shift, right? And we'll talk a little bit more about that again later on. But because the threshold voltage is going to shift, that means that, exactly where the nonlinearity occurs is also going to shift, okay? So in a lot of places, you may not exactly want to use a MOS capacitor simply because of these nonlinearity issues. But there are some places where it's basically fine. As an example, in places like, let's say, a Miller compensation capacitance, where you know pretty well what the voltages on the two sides are, and you can kind of guarantee that there's a big difference there, that might be a reasonable place to use. And again, if it's something where, sort of don't care all that much about the absolute value, also that may be a reasonable thing to use. The other place where it's very, very common is so-called bypass capacitors. So again, this is one of those things that hopefully all you guys were told, back when you first took any sort of electronics course. They said, oh, okay, you've got some chip on your PCB or your breadboard or whatever it is. Make sure you put some cap next to it from the supply voltage to ground, right? And the purpose of that was just to make sure that at high frequencies, you still had sort of a path to actually get some charge onto the chip, right? So the supply doesn't collapse very quickly. So same thing is true even on your chip, and oftentimes that's sort of exactly what you'll use these MOS capacitors for. And for that purposes, it's pretty good, right? Because supply voltage should be pretty stable. So you can keep the thing essentially in inversion, and so the cap is relatively constant and sort of does the job that you want it to do, okay? Any? Yeah. So you're saying, well, okay, why don't we take the bug and turn it into a feature? I can kind of use this as a varactor because it's nonlinear, and so I can move the voltage on one side and kind of get it to behave as a voltage-controlled capacitor. That's also absolutely true. There's a little bit more fun you get into when you really do that, but that is indeed true. Any other sort of questions on this, or? Okay. So now I just wanted to sort of briefly, just like we talked about in resistors, how there's lots of issues in really doing the layout of these things. Because again, as you might expect, what you often end up caring about is the ratio between different capacitors. And so just like we said with resistors, if you really want to get that right, you better use sort of a unit element type of layout. Okay? Not only that, of course, just like, again, with the resistors, you better be careful with essentially putting things around the edges to make the environment look uniform. Right? So you're often going to use things like dummies just to make things look uniform. Now, unlike with resistors, with capacitors, there's actually sort of even more first-order effects in terms of if you put stuff around it. Meaning, if I put stuff around it, I'm actually going to change things more directly than I did with resistors. And just to be clear, that should be sort of obvious simply because with capacitors, if I put one piece of metal here and one piece of metal there, and then I just go and happen to add another piece of metal over there, right? Well, if that was the cap that I used to want, well, now all of a sudden, I'm going to get that extra parasitic from that extra piece of metal that I added on the side, okay? So with capacitors, again, you have to be really pretty paranoid with how you lay these things out to make sure that even all of these sort of basically fringing or things off on the edges don't screw you up in terms of matching things, okay? So this is just one particular example of a capacitor layout. There's actually two capacitors inside of here. So just to make sure sort of everything makes sense, anybody have an idea what the heck are these sort of like funny little knob things sticking out from each one of those unit elements there? Why might I do that? And by the way, just to be clear, this thing might be just like two metal layers kind of on top of each other. So we're looking at like the top or layout view here. So why might I have those little like knob things just kind of sticking out all over the place? You guys have done this before, so somebody who hasn't done it before. Not that I don't want the answer, but
So that the unit element can connect to other unit elements without you having to draw something extra.
Okay, you're going very much in the right direction. So what you said was, I want to have these things so that the unit element can connect to other unit elements without having to draw something extra. So what's the problem with drawing something extra? What issue would that create?
Change the area.
Okay, it would change the area, but I'm actually looks like the area of these little knobs isn't too big of a deal. So you're right, but I'm not sure that's the critical issue. So what else? What else would be wrong?
It'll change the fringing cap too.
Yeah, basically it's going to change the actual capacitance you get, right? Because if I have one thing that, let's say, has a connection that way, and another thing that, let's say, has a connection that way, not necessarily going to have the same cap, right? So the people that did this layout, they were just sort of clever. They came up with this unit cell that had these little knobs sticking out things so that when you connected everything together, if it was supposed to be connected, then very naturally it was included inside of the unit cell, right? And so that everything should, at least to zero order, basically match what's going on, okay? So by the way, just to be clear, what's the ratio between the two capacitors that we were trying to implement in this particular thing here? Like how big was, let's say, C1 and how big was C2? There are indeed two caps there, so.
7-2?
Yeah, it's 7-2. Okay, and just for those of you guys who didn't see that, one of the capacitors is laid out like that. Okay, and the other one is just this piece in the middle there. So there's 2 unit cells in the center and 7 around the edge. So it's a 7-2 ratio. Okay? And like it says on the slide, we're using these sort of common centroid kind of techniques. Again, just so that if there's any gradient, we're going to knock that off as well. Any questions on this? Or? Okay, good. So, as Dan was mentioning earlier, sometimes you can indeed get a so-called MIM capacitor. And so, by the way, this just stands for metal insulator metal. As we'll actually talk about in 1 second, a MOM capacitor, which is a metal oxide metal. Don't ask me why they decided insulator is different than oxide, but whatever, same thing. Just keep track of it, and you'll understand what's going on. So the idea here is that if you really wanted capacitance, then you could do something like the following. You could just take sort of two metal layers and then give an option where you have a pretty thin oxide in between the two. So if you sort of look at a side cross-section of something like this, it'll usually look something like sort of what I'm drawing here. So if this is like the standard spacing you have between your metal layers, this would be sort of the MIM capacitor, where they're just intentionally thinned that down, and they maybe even use a slightly different insulator material there, just to get you higher capacitance per unit area. Okay? And so as we were kind of hinting at before, this did indeed used to be a fairly popular option in terms of, things that people would give you in the process. Because basically, again, if you wanted to get really a reasonable amount of capacitance, then it was too expensive to go and pay for all the extra area that you would need to do it the other way. And so they gave you this option, and on the net, it turned out to be a little bit cheaper. But again, as we talked about, these days, not quite as popular. And the reason for that is kind of the following. So these days, we've actually got a lot of metal layers now. Okay, and so because I have a lot of those metal layers, I can actually do some pretty clever stuff to get some really high capacitance densities even without sort of doing anything to change the process itself. Okay? So to understand how we might do that, let's just sort of take a look at a couple of different options here. Okay? So what I'm going to do here is I'm basically looking at, in some sense, I really only have sort of two options, although, I'll talk a little bit more about that in a second. If I wanted to build a capacitor, then there's kind of one of two things I could do, right? So either I could draw these big horizontal slabs, like we had been drawing before, right? And I could just kind of like spray that over as much area as I need to get the capacitance I want. And then, of course, if I have multiple metal layers, stack all these horizontal things on top of each other. Or I could turn it on its side, right? And then basically, here the picture is not exactly correct, but really what I would have is I'd have a bunch of these metal layers that I would stack on top of each other, and we'll show this in a second, but maybe I'd even sort of connect them all together with vias. But basically, I would try and create like a vertical wall of metal, right? And then keep repeating these vertical walls to get all the capacitance that I want, okay? Now, by the way, it turns out you can do even sort of better than this. You can come up with these like fractal geometries that you can prove have the highest density you can possibly get. Don't worry about it. Nobody does it. It's kind of a pain, but it's an interesting academic experiment. So, between these two sort of vertical and horizontal, and of course, again, you can come up with combinations of these. If I forced you to pick one of these two, and let's just leave ourselves as talking about one layer for now, okay? And obviously, we'll talk about multiple layers in a second. So which one of these two do you think you would prefer, given the characteristics of most CMOS processes these days? And obviously, explain why. Well, actually, we'll come back to you. Maybe we'll take like a real quick vote first just to get the discussion going. So who likes the vertical? Okay. Who likes the horizontal? Okay. So for those of you guys who like horizontal, why do you like horizontal?
I can control the thickness better of different layers rather than the horizontal thickness. Sorry, the vertical thickness rather than the horizontal, because that would involve etching and there's.
Okay, so I guess I sort of agree, except that I don't know about you, but I don't own a fab. And it's the fab that controls the thickness. Right, so I'm a designer. I want to make this thing as good as I can. Now, you're actually sort of going in the right direction. Maybe in terms of control, I don't know, maybe you might be right. But I just want density right now. Okay? So now, I guess, for the guys who voted one way, they perhaps know the answer. So who else said horizontal and why? What did you think was good about horizontal? usually somebody just says, well, I understand that one better, and so I just want to use that. Yeah.
Because it's linearly controlled, so if you increase the area, you can increase the capacitance.
I can do the exact same thing with a vertical, actually. Right? So vertical, it's not as obvious, but actually I'll just sort of show you the picture here. The way I control the extra capacitance with area is I just add more of these tall columns, right? So if I double the number of those columns, I double the area, I double the capacitance, right? So that I can actually do with a vertical. Now, okay, maybe for the guys who know, why do I want vertical? So sorry, this time the majority was not the right answer. So why do I want vertical?
Minimum feature size?
Okay, you're kind of hinting at it, but let's be more specific.
You can control the thickness by the minimum feature size. So, I mean, the horizontal, you're restricted, but like you can use the minimum feature size to your advantage in it.
Okay, so you're basically going in the right direction. So let's just draw sort of the two options here, right? Okay. So let's say this is my horizontal parallel plate. Okay? So as you were just hinting at, that thickness right there, or really that height, that's totally set by the fab, right? So if I'm a digital fab, what do I want to make that? Do I want to make that relatively small or relatively large? What do you guys think?
Small.
I want to make it large. Why do I want to make it large? Again, I'm the digital guy.
You don't want cap.
Yeah, I don't want cap, right? Because if this is small, then whenever I do something like, metal 1 wire and metal 2 wire running on top of it, I'm going to pick up a lot of cap wherever they cross, right? So making that thin, from my standpoint as a digital guy, that's bad news. That's kind of useless, right? That just hurts me. In fact, I might even do things like, by the way, this thing is called usually the interlayer dielectric. I might even use something with a lower dielectric constant that actually has like holes in it or is porous or whatever. I really don't want capacitance there, okay? I'm going to make that relatively thick, and I'm going to try and make it low, basically low K. That's kind of bad news if I actually want capacitance, right? Now let's actually take a look at the alternative. And still looking at the side view now. So let's say I'm going to do the vertical parallel plate. So now my capacitor is going to look something like that, meaning I'm going to take a bunch of these vertical lines and just sort of keep repeating them, right? So now, as we said before, that thing right there, which is usually referred to as the width, that's like my minimum process feature size, right? And of course, this is the spacing. Right, so if I'm in, let's say, a 90 nanometer technology, if I make that on the metal 1 or metal 2, that's probably, I don't know, 0.13, 0.14 microns is kind of the minimum sizes I can get away with there. So by the way, if I'm a digital guy, I want to make that small. Why do I want to make that small? I want to make actually both W and S small. Why is that?
That's your whole job?
Well, not quite. I mean, maybe, but why is that my job? So what's good about that?
More transistors.
Okay, you're actually going in the right direction. So if I wanted to build like a 1 billion transistor chip, not only do I have 1 billion transistors, I've probably got about 10 billion wires. So if I make W and S small, I get more wires, right? For the same unit area, I can pack more wires in. So now, as an analog guy, why is that good news for you?
More cap.
More cap.
More cap. Right? Because the smaller that S is, the more cap I get. And in fact, by the way, the smaller that W is, the more cap I can get per unit area too. Right? Because I can pack more of those lines in per unit space. Okay? So actually, exactly for those reasons, that's why people do like to use these so-called MOM capacitors. And they indeed have this vertical geometry, 90x% of the time. Okay? So this is just sort of how you kind of physically lay something like this out. This is just the picture on one metal layer. So this is like terminal 1, that's terminal 2, right? And then you could just stack a bunch of these things on top of each other. And again, for exactly the reasons we just discussed, You can get a lot better density by doing this simply because the sort of x, y dimensions is exactly what the digital guys want to push to make as small as they can. Okay? So just from a side view to sort of make it clear how this thing works again, what you will typically do is in each one of those sort of, let's say, columns, you really do want sort of this vertical wall of metal, right? Because you want to get all the capacitance you can in between that entire height. So the way you'll typically try and build something like this is you'll have your sort of metal piece on each point, and then you'll draw vias to just sort of staple everything together, right? So it's not that it's really sort of a solid wall of metal, but it's kind of close, right? And there's actually some sort of nice pictures you can draw for yourself as to what exactly this looks like. But that's basically the way you'd really build something like this up. And again, obviously, the more metal layers I have, the more density I can pick up, because the taller I can make each one of those little columns there, right? So per unit area, I get more capacitance, okay? Now, as we've been talking about before, the parasitics, or the bottom plate capacitance, that's really going to be sort of mostly set by your spacing from the substrate down at the bottom over there. And so in some cases, you indeed might actually want to chop off some of those lower layers just to sort of reduce the relative bottom plate. But again, the thing you have to be careful of is when you chop that bottom piece off, you also get less capacitance per unit area. So again, you can actually do a pretty straightforward calculation to see, is it better for me to actually use that and get the extra capacitance and so have smaller area, or chop it off and get the lower sort of per unit area bottom plate, but have to use a larger area of capacitance, okay? Now, by the way, the other sort of piece of good news is here that because this is really set by lithography, and again, the digital guys, they do want some accuracy on that. The accuracy and the matching you can get on these capacitors is actually pretty darn good. So, 0.1, 1% kind of numbers, pretty easy to do. And again, it's simply because it's in the digital guys' interest to make that good, so we can exploit that as well. Okay? Any questions on this before we move on? Or? Oh, so actually, you're going to be calculating that in your homework. But just to give you an idea, you can get even in, let's say, a 90 nanometer technology, you could probably get between about 1 and 2 femtofarads per micron squared. And if you took this to, let's say, I don't know, 45 or even 32 nanometer technology, I've even heard of people getting all the way up to 4 or 5 femtofarads per micron squared. So not as high as, let's say, a MOS capacitor if you were to, absolutely shove everything full of MOS. But it turns out actually even modern processes, you can't even do that anyways. So you can get actually some pretty competitive densities. There is one piece of bad news though, which is if you do that, you can't route anything anywhere through that, right? So you have to have this big wall of just, okay, nobody goes through me, right? Whereas with Mosfets, you can route over them, you can sort of throw them any place that happens to have blank wiring or whatever, right? So that there is that trade-off, but densities are actually pretty good.
Use vias, don't you have to space those walls more far apart?
It's a great question. So you're absolutely right that if I really do put the vias here, in many processes, what I actually end up having to do is if I look at the top view, if I look at the top view, if before I could have drawn, let's say, 2 metal layers or 2 metal lines, each of, let's say, 0.1 micron with a spacing of 0.1 micron, if you put the via in, it's oftentimes wider than that. And so you might have to actually space things apart. So you're right, actually, there's sometimes even a design trade-off from that standpoint. Now, if you don't put the vias in, then you have a sort of interesting mix between the horizontal and the vertical often. Because if you think about it, if I don't have the via, and I have a structure that sort of looks like this, and I'm just going to label the terminals as 1 and 2, I would probably want to do something like that, right? In other words, sort of do this checkerboard kind of pattern, right? And the reason I want to do that is because I want to get both the horizontal and the vertical parallel plate components, and of course all the fringe and etc. as well. So you can do it. The bad news is this is kind of a pain in the ass to hook up. and you can kind of see that just maybe visually, but it's possible, right? So you sort of usually have this mess of wires at the edge of this thing to actually make it work, but that is indeed something that's possible. And again, if you're interested, actually go take a look at last year's homework and problem number 2. It was exactly a question about, okay, do you want to do this or stick in the vias? Any other questions? Okay. So before we sort of, just like with resistors, anytime I drew a resistor, I always got some parasitic capacitance. Well, guess what? If you build a capacitor, you're always going to have some parasitic resistance. Okay? Just fact of life. So if you want to model that, just like with sort of resistors, you could sort of stick little caps at each one of the terminals. Same thing here, right? You could basically just take these little incremental resistors and put those along the length of your capacitor and just break that capacitor up into different pieces. In other words, you can kind of do this so-called distributed model. Okay? Now, by the way, this is also true for resistors as well. Even though we've said we only have resistance and capacitance, and that they both sort of always go together, in fact, they all also come with inductance too. The good news is that in 90x% of the things that you're probably going to do as a mixed signal designer, the frequencies are such that the inductance just doesn't play that big of a role. Because in other words, it's always sort of about the relative impedance, right? And the relative impedance of an inductor is omega L, whereas the resistance is just R. So if you're at reasonably low frequencies and your inductors aren't intentionally large, then most of the time you can kind of ignore that. Okay? But the fact that you have resistance and capacitance together, that almost always kind of comes into the picture. Okay? So one particular thing that, again, we had sort of talked about a little bit last time, but which we'll come back to and just make sure it's really clear here is, let's say I have a resistor, and I really want it to be a resistor, but unfortunately, it also has some capacitance associated with it, right? Well, as we said before, what's going to happen is that if I have something like that, then rather than my impedance just being set by R, it's actually going to start dropping as soon as those capacitors come into the picture, right? Because at high frequencies, the impedance of the capacitor sort of approaches 0, right? So actually, oftentimes, this has a pretty direct implication on even sort of your designs and how you're going to lay that resistor out, okay? Because let's just use a simple example. Let's say that I'm using some poly resistor or something like that, and I'm going to draw just the top view sitting over sort of the substrate. So let's say these are my contacts here, and that's my poly. So what width do I generally want to choose from a sort of resistance standpoint? So let's say, this is contact 1, that's contact 2. If I want to make a big resistor, what width should I be choosing for that piece of poly right there? I want a big width or a small width? Yeah, I want a small width, right? Because the smaller I make that, then the more sort of per unit length resistance I get. Now, what's the bad news? What's going to stop me from making that sort of as small as I want to?
Inductance.
I'm not so sure about that. That's kind of not going to change that much. There's, again, there's something really simple that, is going to come into the picture here.
The minimum feature size again?
Okay, there's a minimum feature size again. I claim actually maybe even something else is going to come into the problem. And so that's right, that's the absolute limit. What else is going to stop me?
Electromigration.
Ah, there we go. So let's say that I wanted to put a, I don't know, we'll be aggressive, a 0.05 micron wide, piece of poly there. So I just want to take like my gate in like a 45 nanometer technology. Well, if I'm going to be running, let's say, I don't know, 2 milliamps of current through that thing, unfortunately, you're going to get what's called electromigration, which is basically just, currents flowing through the thing. The electrons hit the atoms inside of that material. And if you've got enough current, they hit the atoms enough time that actually the line just eventually sort of, instead of looking like that, maybe looks like that. Okay? So bad news. In other words, it doesn't work anymore, right? So if you've actually got some current flowing through the thing, that means you have to use some width for that resistor just to spread that current out over enough, basically, atoms. Okay? Now, why is that bad news from the standpoint of, my whole thing here was talking about capacitance and things like that, so, Why is the fact that I actually have to use some finite width bad news, other than obviously it makes it so that I have to make things longer too? How does that affect the capacitance?
Bigger capacitance per length.
Yeah, I have bigger capacitance per length, A, and B, I have to make everything longer, right? So I've actually taken a double whammy. So in fact, if I look at sort of width, the capacitance I'm going to get for sort of a given resistance is going to go up quadratically with that width, right? Because again, it's wider and it has to be longer. Okay, so if you look at some of these plots here, what they're really trying to tell you is, okay, if I had a 1 micron wide 10 k ohm resistor, it works just fine at 1 gigahertz, which is over here. But if I take it up to like 5 microns, even though, over here you can't even see the effective capacitance, as soon as I do that, well, now actually, at a gigahertz, forget it, it's totally a capacitance, right? It's, the impedance is dropped by, I don't know, a factor of 5 over there already, right? Now, by the way, this is, what's shown here is that this dotted line, which is the so-called lumped model, that's pretty literally me just doing something like this. This blue line is if you really did like an electromagnetic simulation to see what exactly is happening. But bottom line, they look pretty darn similar, right? So, the distributed thing is maybe slightly not as bad, but long story short, they're both bad. Okay, so from a design standpoint, you always want to make that width as small as you can to handle the current. And anything more than that, it's going to be really hard to actually get a high resistance. Okay? Does this make sense to people, or? Good. So the other thing, as we've been talking about, if there is some resistance associated with that capacitance, which is now we're talking about the flip problem, right? So here with the capacitor, I want a high impedance, or more specifically, I just want to store some charge somewhere. But if I have some resistance in there, then I'm basically going to be losing energy, right? So if I really don't want to be losing energy, which again oftentimes is what you want, then I better be careful to include all the just, sort of resistance that I have along these strips of metal. Because, they're metal, but they're not infinitely conductive. Now again, you can get into sort of all kinds of interesting phenomenon about if you looked at high frequencies and you really drove this thing from sort of one side, you'd see this sort of, decaying current profile as the thing, sort of flows in the different loops of the capacitor there. But probably actually the more important thing from a practical standpoint in the things that we're going to work on is if you have something where you really do want a capacitance that has low series resistance, one of the best ways to do that is to actually contact it from both edges of the capacitor. Okay? So again, just to be sort of clear, why is it that contacting from both edges is actually a really, really good idea? And I've already claimed here it drops the resistance by a factor of 4. Why does that happen? Any thoughts? It's actually a very simple geometric argument. So just to be clear, if I used to have a wire that was like this, I'm driving it, let's say, on one end, and I want to know the total resistance there. So let's say that's just some R. Why is it that if I actually was to do the same length wire, if I drive it from both ends, I claim the effective resistance is going to go down by 4.
Is it more consistent current density?
Okay, that's true, but I'm not sure that, it's actually sort of even simpler than that.
0.5 R in parallel.
Yeah, there we go. So all I'm doing is drawing a line in the middle here, right? So if before the whole thing was R, each one of these is R over 2, right? Well, now what do I have? I just have two things of R over 2 in parallel, right? So I get R over 4. Makes sense. Now, there's one minor issue here, which usually somebody at this point says, what the heck are you talking about? Like, how are you actually going to get this to work? So what's the quote-unquote minor issue here?
Directions different.
Oh, well, yeah, you're worried about matching. That's right. There's something, again, very practical.
You'd have to route around.
Yeah, I somehow have to get the signal on the two sides of the wire, right? And if I have that wire there, I don't know why I can't, what's going on. Now, turns out this isn't a horrible thing. sometimes you can actually arrange it depending on what exactly it is that you're doing, then indeed you really can drive it from both edges. Okay? Again, if it's something that you really care about, then indeed you will want to contact on both edges just to reduce that resistance. Okay? Does this make sense to people? Or? Okay. So just to sort of briefly wrap up on our passive discussion, since we talked about resistors and we talked about capacitors and I just really briefly mentioned them, we do need to say something about inductors. Now again, most of the time you're probably not going to be using them. And the main reason for that is just that, well, actually there's two main reasons. A, they're usually just too darn big. Okay, they take a lot of space. And B, and maybe more importantly, they're a real pain in the ass to use. Okay, so if you thought this capacitance stuff was annoying, the inductors are like 3 times or 5 times more annoying. Okay, because you have to know sort of exactly which loop the current is taking, and how long that loop is, and how the fields couple. It's a pain in the ass. Okay. Now, having said all that, it's not to say that there aren't some advantages for using inductors, even in so-called mixed signal designs that we're going to be interested in. So, just to maybe make that clear, anybody ever heard of shunt peaking? Raise your hand if you've heard of that. Or series peaking? 1 or 2 people. Okay, so I'll just maybe really briefly explain it. So it turns out inductors kind of have this slightly magic property, which is that if you add just the right amount of inductance, you can actually make it look sort of like a quote-unquote negative capacitance. Okay, and I'll walk through exactly physically how this really happens in a second, but it turns out that if I compared this amplifier that I've drawn right there versus this amplifier here, for the exact same amount of current, I can actually make this amplifier with the inductor about 50 or 60% higher bandwidth. Okay? And actually, if I added another inductor right here, then I think it's even like, maybe that 85, or I don't remember exactly, maybe it's like 150 or 200%. Okay? Exact same amount of power, nothing different other than just I added this inductor in. Okay? So the way that works is something like the following. So let's look at this original amplifier right here. And let's just do even something very simple. So let's say I have a little, change of voltage at the input over there, right? When I do that change in voltage, that's going to draw some current through the transistor, right? Well, so some of that current is going to come out of the capacitor, and initially maybe a reasonable amount of it comes out of the capacitor, but some of it's going to have to flow through the resistor too, right? Flowing through the resistor actually kind of sucks, because if I want to do something quickly, I want to pull all the charge out of the cap, right? That's the way I get things to move quickly, is I just shove as much current as I can only through that capacitor, right? Well, so now you guys tell me, how is it that this inductor can actually be a good thing then? What's it doing? Yeah, it's suppressing the current through the resistor, right? So it's basically making it so that initially there's not really that much current flowing through there, so that all of the current gets shoved out of that cap. Okay? That's exactly why you can use this trick to actually get effectively higher bandwidth. Okay? Now, it's not totally for free if you sort of draw the transfer function of this thing. If this is what the RC amplifier used to do, the so-called shunt peaked amplifier, and again, it depends on how exactly you design it, will probably look something like that. Okay? Which means that, it's not exactly flat anymore. In fact, there's all kinds of equations you can come up with for trading off how flat this thing is versus how much, phase response errors you get and things like that. Long story short, it's it's something that you can kind of play around with. It's a little bit more complicated. But every once in a while, you will indeed see something like this, even in a so-called mixed signal design, simply to just try and up the bandwidth beyond what you could have done otherwise. Okay, and if you're really pushing on the edge of the technology, that might really be a good thing to do. Okay?
So what kind of inductance values would something like that need?
It's a good question. So it depends on the capacitance, obviously, or really the relative impedance that you're driving. The good news is you tend to need reasonably large inductance, maybe not huge, but sort of reasonable size. The really good news is that because I was going to put a resistor there anyways, I don't need a very good inductor. In other words, even if that inductor has a lot of series resistance, that's actually okay. So in fact, the way you can build that inductor, and this is a couple of examples here, is with these so-called spiral inductors. In fact, you can be more clever than this. You can do things like turn the inductor through multiple metal layers, right? Almost like a sort of toroid or solenoid kind of thing, right? Again, as long as you don't care that much about the resistance, that's a pretty easy thing to do. Unfortunately, if you really wanted RF inductors, there you care about the resistance, and so you can do all the things that I'm showing here, and in fact, that's what you have to do. But people spend again sort of entire PhDs on just how can I get the darn resistance of this thing to be smaller than it used to be. Okay, so I'm really showing this only so that when you see these things on dye photos, you know why this and why there's these weird spiral things sitting there. For probably the rest of the class, we're not going to spend sort of a whole lot of time on these because most of the time you probably won't be using them in mixed signal designs. So, any sort of last questions on passives, or should we get started on MOSFETs now? Okay, well, as I said, this is not the end of the story. You're actually going to be spending lots of your time playing with passives, so, keep some of this stuff in mind because from a design standpoint, this really is things you're going to be applying over and over and over again. Okay, so let's go ahead and move on to start talking about MOSFETs. So, as if you have the handout there, you've sort of seen it's not just that we're talking about MOSFETs per se, but actually we're going to be talking about models. Now, again, if you were anything like me when I was a student, you'd sort of say, well, darn it, why are we talking about models yet again? I mean, you've probably seen this in 3 or 4 different classes now, right? And every time we told you about some MOSFET model and then maybe 3 other things related to the MOSFET model, and by this point you probably are like, well, darn it, I really don't care anymore, right? I just want to build circuits. Well, okay, bad news. If you're going to do analog circuits, you got to know about some of these things, okay? Because long story short, if you're doing an analog circuit, the precise behavior matters, right? Because exactly what current I have and exactly what capacitance I have and which elements the current is flowing through and things like that, all those are kind of important now, right? Those are all things that we probably are going to have to think about. And by the way, the reason why in digital you can kind of get away with it is because you just have larger margins of error, right? You sort of built digital in the first place to be able to tolerate mistakes, and so it's kind of okay if you don't have that great of a model for the transistor. Okay? Now, the other reason, which is, again, sort of why I'm going to be spending some time talking about models, is the real important point here is that these models are going to let us sort of come up with some intuitive reasoning about the circuits that we're going to build. Okay? And having that intuitive reasoning is really, really important. Because, you can run a lot of experiments with SPICE, but, SPICE is, again, it's a computer program, so it can give you bogus answers. And unfortunately, if you wanted to actually go and really do the experiment, meaning build the circuit and then just go and measure it and see what's wrong, that usually involves about a 3-month, fabrication turn time. And depending upon what your technology you're talking about, even if you're just like a student, probably anywhere between $40,000 to $100,000 per chip that you want to tape out. Okay, so as you can imagine, unless you have, an advisor with lots of money, and if you do, tell them to give some to me, you're not going to be spinning this thing 10 different times, right? You want to get this darn chip right the first time. Because, again, you don't want to be spending your advisor's money, or maybe when you go and you work in a company, it's not $100,000, it's $1 million. There's not that many times you want to do that, okay? So the reason we're going to spend some time talking about basically CMOS transistors and how you model them is really to build up some intuition and understand sort of how things are supposed to be working, okay? So I talked about this a little bit before. The point of a model is really to abstract away some of the details. But again, in analog, the sort of the best abstraction for you to use really strongly depends on the question you're trying to answer. Okay, and this is particularly true in analog. In fact, it turns out it's true even in sort of digital, right? Because in digital, if all you cared about was just what's the function of a particular circuit, usually you can just pretend that the transistor is a switch, a voltage-controlled switch, right? Usually that basically gives you the right answer. And okay, maybe if you really care about like performance, you'd say, fine, it's not a switch, it's like a current source in a switch, right? And maybe some capacitance. And that usually gives you kind of the right answer. So the thing that we're going to be spending some time on sort of today, but really throughout the class is, for analog stuff, what's kind of the right abstraction for me to use, given a set of different questions that I might be interested in. And at the risk of stating the obvious, it's almost never going to be, I want to have BSIM in my head and just, run BSIM and get these thousands of parameters and get like the last, order of magnitude sort of accuracy there, right? And obviously you also don't want to just go and like take a bunch of IV curves and measure them and just have those IV curves and have the lookup table in your head, because neither one of those obviously works particularly well, okay? So again, given that we're talking about modeling, we should always sort of start out with our good old friendly square law model, which again, I'm sure you guys have all seen like 5 times by now. And it's not that I dislike this model. Actually, it's a very useful model just from the standpoint of thinking about things. But as we'll talk about in a whole lot more gory detail as we go on, unfortunately, it's grossly inadequate to fix all kinds of just issues that are going to come up, okay? And a lot of times people refer to these as so-called short channel issues. A lot of times it actually has nothing to do with being short channel per se, but we'll go through that in a little bit more detail. There's actually another thing that this model really doesn't do very well, which increasingly is actually becoming an important problem. And that's that it doesn't handle at all what's called moderate inversion. And what I mean by moderate inversion is, let's say that VGS is somewhere close to VTH, okay? Well, probably many of you have seen sort of what happens when you go below VTH. If not, we'll talk about that some more. Many of you, even if it was a long channel device, then okay, I could have used, the square law model, but it turns out right near the middle, there's kind of weird stuff happening because you have to mix between a couple of different regions of operation. And it just so happens to turn out that these days, that's actually kind of an interesting region to be sitting in, okay? So just before I sort of dive into all the gory, nasty stuff that's going to happen to us, and again, I'll explain why I'm going to do that, I just wanted to do one really sort of quick thing. So when I have this square law model, the most important thing to remember, and in fact this is true of sort of any model, is that what really is going to be setting the current through our transistors is basically just sort of 2 things, okay? Those 2 things are always just going to be how much charge you have in the channel and how fast that charge is actually moving, okay? So I claim that basically all the effects we're going to talk about are somehow related to one of those 2 quantities, okay? So by the way, maybe somebody who took 141 or just happens to know it, given that this is exactly that it's always charge times velocity, why is it that there's this x squared here in that good old square law model? Like, why is it that the current is dependent on VGS minus VTH squared? What's going on there? Anybody remember?
Charge and velocity are both dependent.
Yeah, exactly, right? So charge, we just have our sort of good old MOS capacitor, right? So the charge that I get sitting in the channel there is proportional to VGS minus VTH, right? And once I get into saturation, which means I get, pinch off or whatever, then the effective voltage across that charge ends up being also VGS minus VTH, which, at least ideally speaking, means the velocity, or the speed at which that charge is moving, is also being set by VGS minus VTH, okay? So it makes perfect sense. I get something that's sort of quadratic. Now, obviously the bad news is, when we get to the real transistors, it's not exactly going to behave that way, but if you can partition it into the 2 things, you can really quickly understand what it is that's happening and sort of why it's changing things the way that it is, okay? So, okay, there's this whole long list of assumptions here about, how you get to the square law model, all of which, of course, are wrong. So maybe to give you a hint as to why they're wrong, I'll maybe just sort of show you what a so-called modern transistor actually looks like these days. Okay, so this is perhaps a little bit, sort of difficult to decode, but maybe I'll just walk through it really quickly. Okay, so If I look at a modern transistor, this is actually the piece of poly in the center here. These things on the side are so-called like spacers or capping layers. Those are just to sort of like make sure that everything is lined up correctly. Okay, but maybe the first thing that's sort of important there is this thing that you basically can't even see there. That's the gate oxide we were talking about before. That's that 1.2 nanometer thick kind of thing. And so if you didn't used to believe in quantum mechanics, just go take any modern transistor and measure. Just put a voltage between its gate and its source, and you'll suddenly see some magic thing happening. You're actually going to have current, okay, even though it's a quote-unquote capacitor. Turns out, with a 1.2 nanometer thick thing, it's thin enough that you can actually tunnel electrons through that thing, okay? And in fact, the more voltage you put on there, the more tunneling you're actually going to get by an exponential amount, okay? So right off the bat already, that thing that was always so nice about Mosfets, about, you could tie all kinds of stuff to the gate and not worry about it. Well, now you actually have current flowing through there, okay? So I'm spending a little bit of time on this one. I'm not going to go into a lot of detail later. I believe the model we have in our class right now doesn't even include it. But user beware, because most any modern technology you work with is going to have pretty appreciable, basically gate tunneling current. And you better know that it's there, because if you don't, and the model doesn't include it, when you build your circuit, all kinds of nasty things could happen simply because you just didn't realize that, things were drawing current all over the place. Okay, so keep that in mind. There's also obviously, you can see the channel here is actually quite short, and we use reasonably high voltages. So that's going to create all kinds of interesting sort of so-called short channel effects, things like velocity saturation, some other things as well, like basically punch through and drain-induced barrier lowering. But long story short, there's all kinds of sort of interesting things that are going to be happening here. So basically what I'm going to do in the next sort of slides, and we'll finish this up next time obviously, is I'm going to walk through what I think are a few of the most important effects for you to know about. And the way I'm going to do that, I'm going to sort of categorize it into which sort of physical parameters does it have the most direct impact on. And again, it's not that I'm saying that you should be running SPICE in your head, but I want to walk through these things because if you don't know to expect to look for them, then again, you might get some bogus model or you might build some circuit and just be really, really surprised when it doesn't work. Okay, so let's just maybe quickly start out with, there's one other thing. Well, so we'll get into one of the sort of effects there, and we'll come back to it. Okay. So first effect that's kind of interesting that you may not have seen before, or really the first sort of device change, is that if you look at any modern transistor, usually we draw these pictures that just have these nice N plus, and then another N plus over here, and the gate oxide, and etc. Turns out you don't actually really do that anymore. What you actually do is you have some pretty complicated doping profiles all around this region here. And in particular, what's really common is these so-called halo doping profiles. Okay, and don't exactly ask me why it's a halo. I guess somebody thought that looked something like a halo. I don't know. Don't ask me. So, why would you do something like this? Well, basically, remember there's always some depletion region over here, right? And if I have a really short channel device with, without too much doping, then what's going to happen is, if I'm unlucky, I could actually get sort of the depletion at the source and the drain to touch each other, right? Now I basically don't even have a working device anymore because current's just going to flow straight through there, right? So what do people do? They add these so-called halo doping things because, and these are, by the way, heavily doped. Because if you put a heavier doping in there, it just makes sure that the depletion region is smaller, right? So basically make sure the device still sort of operates correctly. Now, why did I actually go and sort of mention this? Well, turns out this leads to a very interesting effect on the threshold voltage. So probably back when you sort of first took, your basic kind of device physics class or 105 or whatever it was, they said that if I plotted the threshold voltage versus the channel length, what you'd expect to see is something that sort of looks like this, right? where basically below some, not magic, but below some point on the length there, basically those depletion regions get really close to each other, and all of a sudden the threshold voltage just tanks and goes really close to 0. Okay? Well, so when I add this halo doping in, turns out what you're now going to get is something that looks more like the following. Okay? Now, before we sort of explain exactly how that happened, I'm going to claim that actually when people kind of came up with this technique, it was really this effect that they were shooting for. And in fact, this is actually a really good thing from a sort of manufacturing standpoint. So why do I say that? What's actually good about the curve in blue versus the curve in red? Why is it that if I'm a fab, I would actually want to do something like this? Any thoughts?
To increase the amount of money they make, right?
Okay, yeah, that's certainly true. They want to make more money. So how does this help you make more money?
Yield.
Okay, it's going to improve yield. That's actually true. Why? So if I'm a digital guy, you know, what do I want to do with my transistors? What kind of transistors do I always want? Small, and in particular, what do I want on the channel length?
Are you doing the music?
I want short channel length, right? So can you just close the door in the back there? Thanks. So I want short channel lengths, right? If I want short channel lengths, and if I'm the fab, right, what I'd like to do is be able to place my design or my transistors basically right there, right? But unfortunately, if anything minor gets tweaked, I might sort of fall off this cliff, right? All of a sudden, my threshold voltage goes to 0 and none of my devices work anymore, right? Well, if I play this trick here, and now I can park my channel length nominally there, there's this little plateau, right? So even if things kind of get tweaked a little bit, good news is threshold doesn't change all that much. Device actually still works. Now, the interesting side effect of this, by the way, is that now, if you make the device longer, the threshold voltage might actually go down. Okay? And so just really quickly before we kind of wrap up for today, the reason why this happens is something like the following. Okay, so let's say that's my original sort of short channel device with these so-called halo or pocket implants with a P+ over here. So remember, when you have higher doping, that always increases the magnitude of the threshold voltage. Okay? And we usually like to think about things as these, very simple, it's only exactly the surface that matters. In reality, there's some like 2D and 3D stuff going on there, right? So those P+ implants there, they actually sort of are changing the effective doping in the channel. Well, so now if you think about it, if I take the same device design, but I just make the channel length longer, those halo things generally don't change in sort of the spatial extent, meaning the size of those halos is about the same, right? So if you think about it, if I kind of look averaged over this region right here versus that one right there, the average doping here is going to be lower than the average doping there, right? If that average doping is lower, threshold voltage is lower, okay? Which is exactly why if you walk in that direction, threshold actually starts rolling off, okay? Now, obviously, at some point, you still hit the sort of short channel effects and all that, but this is kind of why you start seeing these types of curves here.